Okay, here we are. We're already past our lesson in the textbook. We've gone through sections 5.1 through 5.5. Here is a College Board focused topic, more on integrals. And we'll see a worksheet on that in just a little bit too. But let's read this. We have a graph of f. The fact that it appears to be made of just segments is very important. When you see something, this is going to scream out that you're probably going to have to find some net area geometrically, like we were doing earlier in the unit. And maybe even right now you're saying, yeah, I see some triangles. And that's definitely going to come into play. But let's keep reading here. Here's the graph of f. It's got two line segments. Look at g though. G, if we read this together, g is the function. Oh my gosh, look at this. Look at that. It's an accumulation function. Oh, we're going to see a lot of these. My goodness, we're going to see a lot of these. So g of x, it's this accumulation function. It would be the net area from 0 to x of f of t dt. And tell you what, up high, I'm even going to rewrite this. In part A, we're going to have to find a whole bunch of things. But let me just write this a little bit larger, because this can look a little small. I think immediately kids can correctly question the use of the letter t, because it just looks so strange. I know when I first saw it, it really bothered me when I was a student. I just thought it was ridiculous. Like, why in the world just not put everything in as an x? But here's what's happening. Look at this. The very first thing they're going to say is find g of -1. G of -1 is going to be the integral from 0. Now this x became -1. That means I'm going to make my upper bound become -1. Look at that. But what I don't want to have happen is I don't want the integrand, the inside of the integral. We'd never want someone to think that the inside of that integral is really just f of -1, which would just be a constant if you think about it. Right? F of -1, if this is the graph of f right here, f of -1 is going to be 0. You can see I put a blue dot on that graph. So that's why we're not going to use the letter x inside of the integral. We use this, what we call a dummy variable. Because if we used x inside, it would become f of -1. You'd say, oh, the answer is 0. You're just integrating 0, done. No, that's not what we're saying. We're saying find the net area from 0 to -1 here. Here's your picture. And my goodness, right now this can look so bizarre. Kids can look at this and say, wow, how do you do this? This looks so bizarre because my bounds are out of sorts. My lower bound, 0, is actually bigger than my upper bound, which is -1. Could I flip those? Yeah, you can. We're so used to seeing a smaller number down below and then an upper number, the higher number up high. You bet we could do that, but what do I have to do? Add a negative out in front. And kids will say, do you really want to do that? Yeah, I'll tell you why. You really want to look at this as net area from -1 to 0, but we've got a negative pulled out. Here's though what we're going to see. Look, from -1 to 0, look at that. I've got a triangle. I've got a triangle there. And as we're looking at this problem, wow, area of a triangle. I think we all know, I'm going to write this off to the side, the area of a triangle, what's the formula for it? 1/2 the base times the height. You'd say, well, wait a minute, what is, and I'll put my negative out there, what's my base of this triangle right here? Just 1. What's my height? 3. And before you know it, you'd say, oh my gosh, 3 times 1 times 2, that's 3/2. Wow, -3/2. G of -1 is that value right there. And we've done the first part. By the way, if area is ever below the x-axis, what do we have to do? Make it negative. So, there are two negative ideas that come into play here. We flipped our bounds and we pulled a negative out. Yeah, you can do that and you need to do that. But also, if your area goes below the x-axis, and it might down the road, then we've got to be careful. We're going to have to realize that area below the x-axis is negative. Wow, you know what? You just did the first part of part A. You found g of -1. Hey, wonderful. But then, continuing on, someone will say, find g prime of -1. And you know what? First, I want to find g prime of x. And here is my accumulation function. You know what? You learned how to do this in lesson 5.3. You said, could I take the derivative of an accumulation function? What is g prime of x here? What do you think? F of x. Remember, you'd plug that x in, and look at that. We're done. This is the fundamental theorem of calculus, part 1. It's actually a corollary theorem to it, a little additional part to it, but that's the idea. Wow, take your derivative of that accumulation function, you just have f of x. Wow. Well, wait a minute. Now they're going to say, what's g prime of 1? G prime of 1 would be f of 1. Look at your graph. This is the graph of f. Help me out, guys. What is f of 1? Or is it -1? Oh, wow. Good thing you guys are here. Yeah, and didn't I already talk about that? Yeah, what is f of -1? 0. The graph shows that to you. The graph shows that to you. And f means y value when x is a certain number. It's that red dot right there. There's f. And we're saying, what's f of -1? Well, it's the y value when x equals -1. You can see your y value is on the x-axis. That's where it's 0. You're done with the second part. Oh, my gosh. We doing okay? And then you'd say, well, wait a minute. Now we need g double prime. Now, hold on. If g prime was equal to f of x, what's g double prime of x? F prime of x. I just keep taking a derivative. Do you agree with that? And then you'd say, well, g double prime of -1 would be f prime of -1. And this is where sometimes kids feel a little bit uneasy. They'll say, no, wait a minute. Hold on a second. You gave me the graph of f. And I'm supposed to find a value of f prime. Wait a minute. How did we start this course? F prime really is measuring what is representing? The tangent line slope. The tangent line slope. You'd say, well, what's the tangent line slope from at x equals -1? Well, rise over run. It's this segment slope in and of itself. Rise up how much? 3. Go right 1. Guess what that is? 3. Wow. I can't tell you the number of times the College Board has asked these 3 questions in a row of an accumulation function. Whatever the function is, they might say, find g of -1. Now, sometimes they choose a different number. But then how do they follow it up? What's g prime of that number? And then finally, what's g double prime of that number? Yes?
So if g prime is like the point and then g double prime is like the slope, what is like g of like x represent? Like on the
Yeah, so g of x itself, what does this represent? First of all, g is just a function itself. By the way, we could even graph it point by point. G is the accumulation of net area. So like right now I found out what g of -1 was. I could find out what g of 0 is real quickly by saying it's the integral from 0 to 0. And what's the integral from 0 to 0? 0. And now I could say, when x equals 0, g equals 0. I could say, hey, what's g of 1? Well, g of 1, according to this green accumulation function, see, it's an accumulation of net area of f. That's the way we're defining that function. We're saying, well, what is g? It's an accumulation of net area of that graph that you have right there. So for any x value, like at x equals 1, you'd say, well, from 0 to 1, I've got a triangle. What's my base? It's 1. What's my height? 3. 1/2 base times height. You could say, well, that's going to be positive 3/2. Look, g of negative 1 we found was negative 3/2. And we could keep doing this as long as this function is defined, and we're creating a new function based on the net area that we're accumulating. Okay? Now, there will be real-world scenarios where accumulations actually take place. We're going to get to that down the road. But this is setting the stage. Okay? So, very good. Let's keep going here and see if we could go to B. B says, for what values of x is g on this open interval increasing? So I'm going to come over here to B, and wow, let's think about this. I'm going to say, where is g increasing? I'm going to fill in a little stem sentence here. G is increasing when what is true? Think as a calculus student. Well, when g prime of x is positive, but yeah, Rudva, what you just said is the same thing. You just said the same thing. By its purest definition, a function is increasing when its derivative is positive. What Rudva just answered, and on the video you might not have heard what this young man had just said. He was more or less saying, well, we just saw up above, right in here, I'm going to highlight it in blue, that when we took the derivative of that accumulation function, we just had f of x. G prime of x equals f of x. We're interested where this function f is positive. So that's saying, where is my curve above the x-axis, or above y equals 0? And for what x values would that be true? Yeah, negative 1 to 1. So they're saying, for what values of x is g increasing? You could say g is increasing on the open interval from negative 1 to 1, because they wanted us, pardon me, increasing, wow, always put closed, so sorry guys, always put closed intervals when you're talking about where you are increasing or decreasing, right? For concavity, we always keep it open. So g is increasing on that closed interval because g prime of x is greater than 0 there. Yes? Well, then it would be negative 2 to negative 1 and 1 to 2.
Yeah, but like, wouldn't it say that 1 is both decreasing?
Oh, yeah, I know that's upsetting, because technically what kids will point out is they'll say at x equals 1, g prime, which is f, it's not positive, it's 0, right? And same thing with g equals negative 1. But it has become convention to always put closed brackets. So you're right, we would have closed brackets around 1 and negative 1 for when we're talking about being decreasing as well. You're correct in that. But that has become the convention. And I know, I was even talking to a calc teacher about how that bothers him even right now after he's been teaching calc for so long, but this is just the way that we've agreed to write it out. And you could make a very good argument to say at those values, you're not having a positive derivative. I know, but you could also argue and say, just like I'm holding up my pen right now, my pen's going up from t equals 0 all the way up to maybe t equals 2. At t equals 0, maybe I'm stopped. But I could still say I'm increasing between 0 and 2 seconds. So that's kind of like an analogy why that slides by. Okay? All right. Let's do C. Wow. For what values is G concave down? Well, let's think about this. G is concave down when what happens? When G double prime of X is negative. And guys, we already saw from up above, G double prime of X is F prime of X. We're interested, we want to know, hey, when do you have negative tangent line slopes? You see what we're talking about? When on this graph do we have negative tangent line slopes? So we're going to look at this and we'll say, wow, I'll erase that. Between what X values do you think that's going to happen? 0 and 2 right here, right? That's where you'd have negative tangent line slopes. So I'm going to write that down. We're going to say G is concave down. On the open interval, and kids will say, shouldn't you put brackets around it? Never for concavity. Always keep it open for concavity. Just like for increasing and decreasing, we're going to lock it into brackets. For concavity, we're going to keep it open. So G is concave down. They want you to explain your reasoning. We could say because G double prime of X is negative, it's less than 0 on that interval. Okay, we doing okay? Wow. You could see why this question is so popular for the College Board. Yes?
So knowing that find U of X by A, I made a graph of U of X.
Yeah. Yeah. So that's what Matthias is saying. I don't know if you heard him saying, especially on the video. He's saying, hey, couldn't you just go ahead and, with the information that you could get from net area? Remember, we had Kai asked earlier. It was a wonderful question. That was a fantastic question, Kai. You're saying, what does G really represent, and how would we find it, and so forth. It's a brand new function based upon this. We could get points. We could know what this thing looks like, right? We can actually learn about where it's increasing, where it's decreasing. We can learn about its concavity. We could actually make a really nice graph. And for sure, you can do that. Yes? A plus C would come from taking an antiderivative. We never took an antiderivative. Thank you for raising that. That's a very important issue. A general antiderivative will have an arbitrary constant, a plus C. But so far, we really have never done an antiderivative. But I think that's what Matthias was talking about in terms of absolute extrema. Absolute extrema. Yeah, you could get help and you could actually know what this graph looks like in full detail. But listen, I can tell you this. This is the extreme value theorem. This is the extreme value theorem. They're not asking us to graph. Sometimes they do. Sometimes even on the College Board, they have asked kids to sketch a graph. And that's kind of crazy. It happens now and again. But instead, they're saying, hey, find the extrema, absolute. They don't even have to say absolute because the brackets mean we're going to have to check endpoints. And you're going to see very soon, I'm going to pull up rubrics. If you don't check the endpoints, even if you get the right answer, they'll say take 2 points off. They'll say, what? I got it. You didn't check the endpoints. Done. It's brutal. So we've got to make sure we're going to check our endpoints. But listen, the extreme value theorem meant find the critical numbers. I can't write today. Let's fix that up. Find the critical numbers. And that means where G prime is 0 or where G prime is undefined. Wow. Well, we already know what G prime is from earlier. Look in here in blue. We already saw that G prime is f of x. It's that graph that they gave you up above. And then you could say real quickly, now wait a minute, where is f going to equal 0? Well, at -1 and +1. So here are your critical numbers. X equals 1, x equals -1. Okay? Well, what did the extreme value theorem then say, though? Do I have to make a number line? No. What you do is you check your endpoint into the function, right? Plug your critical numbers into the function, but make sure you're checking both endpoints. Always. And that's something that I'll be grading you on your next test, which is, I believe, going to be not next week, but the following week. It's going to be early in that week. I'll get you the exact date a little bit later. But hey, look at this. The G of 1, you could say we already worked that out. You know, that's when Kai asked about that. You know, G of 1, you said, hey, it was 0 to 1 of f of t dt. You said, hey, that was your triangle. You know, and that's that triangle that we had right in here. And I'll just do that, right, from 0 to 1. We worked that out. G of -1, kids will say, you already did that in part A. You did that in part A. Yep, don't do it again. Don't do that again. You already have it. And you'd say, well, guess what? Now I just have to check my endpoints. So look at the bottom here, G of 2. That's from 0 to 2 of f of t dt. Wow. 0 to 2, you know what? I'm going to maybe highlight this in yellow. I've got from 0 to 1 is here, and from 1 to 2 is over here. Guys, if you're really on your toes, you're going to know what this net area is. 0. Kids go, how do you know that? They're congruent triangles. Both of them have a base of 1. Both of them have a height of 3. But one is above the x-axis. That means its area is positive. One is below the x-axis. That means it's negative. So please hear this. If you see congruent figures, they wipe each other out. I can say very quickly that G of 2 is actually just 0. Wow. Now what? Now we're going to say, well, we're going to go 0 to -2. Oh, wow. That's an eyesore, isn't it? I'm a calc teacher. I've been teaching calc for so long. Let me tell you the truth. I look at those bounds, and I'm like, don't like that. Wow. Tell you what, flip them. Flip them, right? And say, hey, especially for this geometrical problem, if it's all just algebraic, if you've already got your function, you could plow through the fundamental theorem in brute force. You'd get the same answer without flipping. But if you're finding area geometrically, and they're going to ask you to do that, you want to say, hey, these bounds, they're backwards. I better flip them. And then -2 to 0. Wow, all of a sudden kids will be like, Mr. Doubtner, it's the same thing. It's the same situation. Look at this. I've got a triangle down below. I've got a triangle up above. They're congruent triangles. One is below the x-axis, one is above the x-axis. So just like what we saw in yellow, you come over here and you're going to say, you know what? Yeah, the bounds get flipped around, but at the end of the day, you've got -0. Wow, look at that. We doing okay? So we're not done until we write it out. We've got an absolute max of what? 3/2 at x equals 1. We've got an absolute min of -3/2 at x equals -1. And kids will say, so what's my justification? Should I say by the extreme value theorem? Let me be real honest. You don't even have to write that. Your work right here is going to count as your justification. And that can sound weird because for so many others, they get pedantic and real nitpicky. And they'll say, hey, make sure, if you mention the first derivative test, you mention a change in the sign of the first derivative and so forth. We doing okay? Not the last accumulation function we're going to see. For sure, we're going to see a lot of them. But I hope this is making sense. Well, there is a back page. But tell you what, first, I'm going to write in a little bit something different. Here's a claim that if we are given information, like let's just see that we have a graph f prime of x, and we are told the value of a function f somewhere. I'm going to call it f of c. And c is just some x number. It could be any x number. And we're going to see they love to mix it up a lot of different times. Sometimes c is 8, sometimes c is 5, sometimes it's -17. But they will tell you what f of c is. Okay? What I'm going to do right now, this can look so bizarre. I'm going to say f of x is f of c. All of a sudden, kids will go, whoa, wait a minute, Mr. Dobner, that can't be. You're saying that function is just that function value? Oh, we're not done. We're going to say it's the integral from c to x of f prime. Here's that dummy variable again. Wow. Oh, we're going to keep talking about this. Oh, this can seem so weird. First time you see it, no doubt it looks so bizarre. Especially when you say f of x equals f of c. You're almost saying your function is, this constant. Yeah, f of c is just a constant for a moment. Now, understandably, kids are going to say, I'm sorry, with all due respect, I don't believe it. That just seems crazy. How in the world could that be true? Look, I'm not going to ask you to do proofs of this, but I'd like to offer you some support that this is true, because dare I say this could just seem to be unbelievable. Listen, I'm going to let x equal c. So I'll call this part 1. And then you'd say, well, f of c, wow, Mr. Dobner, if you've got that, you're going to say f of c plus the integral from c to c of f prime of t. Wait a minute. What's the integral from c to c? 0. Oh my gosh, this part appears to be true. Wow. Now, please understand something. We really haven't officially proved it, but what perhaps might feel a little bit better, you might say, well, yeah, I do believe that when x is equal to c, that box formula checks out. But, of course, kids could say, Mr. Doubtner, there are billions of x values. Who's to say it really fits every single one? Right? I mean, if you're skeptical, you have a right to be. Let's talk about another approach. You say, take the derivative. Take the derivative. Kids will say, I beg your pardon? F of x equals f of c plus this integral from c to x of f prime of t dt. The golden rule of algebra is what you do to the left side, you do to the right side. That applies to calculus as well, doesn't it? Let's take the derivative on the left. What's the derivative of f of x? F prime of x. Now wait a minute, what's the derivative of f of c? Hold on, f of c is a constant. Isn't it just some number like 17 or 5 or negative 2? That's 0. Oh, wow. Oh, wow. Fundamental theorem of calculus, part 1. What's that? Yeah, plug your x in. Oh, my gosh. Oh, my gosh. It's true. It's true. Who would have thunk it? Wow. Well, I have to show that because, again, if someone looks at that and if they're going, oh, you know what, Mr. Doubtner, that looks insane. That looks crazy. What are we seeing? This accumulation of the derivative, oh my gosh, that's going to build the function. Oh my word. Maybe it doesn't seem so strange before because if you think about it, how will you get to a function? You're going to have to be integrating a derivative, won't you? Right? Maybe it's not as far-fetched as it first seemed. Wow, but I wanted to slow that down. By the way, what you're looking at, page 1, was an actual, real, free response that was given out by the College Board years ago. So is number 2. If we could go back to the right year, this is what students in AB and BC calculus would have had as one of their free response questions. This one, right here. You go, oh my gosh, look at this. It's the graph of f prime. And they're giving us areas. They are being so nice. When you see this problem, you actually might not think they're being real nice, but you don't even have to find areas of triangles. You see what I'm talking about? They're giving it all to you. Holy cow. Who would have thought that they'd be nice? Look at this. F of 8 equals 10. And now, oh yeah, can you tell me this one, and this one, and this one, and this one? You're like, oh my God. Holy cow. You know what? What I put a big box around. What I put a big box around is what I want to jump into right now. And if you need to make a flashcard of this to help you memorize it, that's okay. We'll keep doing it. This is not the last one of these we're doing. But you'd say, well, f of c, they've just given this to you. See, this is f of 8 plus the integral of 8 to x of f prime of t dt. Wait a minute, what number is f of 8? It's 10. Holy smoke. Wow. Now kids can say, how am I supposed to find those 4 problems? Answer with this thing right here. And then we're just going to have to do some quick checking. But this is the key. Notice the dummy variable again inside of the accumulation function. We're not writing that as f prime of x. We're writing it as f prime of t. So they're saying, hey, please find f of 0. Okay, we could do that. According to this, it's f of 0 is 10. plus, oh no, not this again. Now, yeah, let's change the bounds. And when you change the bounds, out comes a negative. Guys, we're almost done. Maybe you see it already, and if you just get what I'm saying, the rest of these are essentially the same problem. It's really just the same exact problem. You're just going to have different amounts of area that you got to deal with. 0 to 8, and kids are going to go, wow, well, 8's over here, 0. You know what? This is positive 2. This is positive 6. This is negative 3. This is positive 7. And what am I doing? I'm paying attention to whether my area is above or below the x-axis. So you'd say, what's the area, the net area from 0 to 8? 2 plus 6 minus 3 plus 7. Right? So look, we can do this real quick. It's 2 plus 6 minus 3. I think it was minus 3, right? Plus 7. Don't forget there's a minus out in front of that whole thing because we flipped the bounds, right? And then you'd say, well, 2 plus 6 is 8. 8 minus 3 is 5. 5 plus 7 is 12. You'd say, oh my gosh, you know what? F of 0, what's f of 0? It's negative 2. You doing okay with that? Let's do another. Here's Roman numeral number 1, right? Then we're going to say, well, hold on, they wanted more. They also wanted us to find what? F of 1. The kids will go, what do I do? Go to that golden equation right there, and go, wow, now I'm going from 8 to 1 of f prime of t dt. Yeah, you know what? Flip your bounds. Kids will be like, it's the same thing. Pretty much. Pretty much. Pardon me. Pretty much, except we're going from 1 up to 8. We're not including that plus 2, if you get what I'm saying. Right? So you're going to say, well, from 1 up to 8, I've got this area, I've got this area, I've got this area. It's 6 minus 3 plus 7. Right? The computer's going a little wonky. Let's see if we can bring that down. So it's 6 minus 3 plus 7. Let me slide that over. And 6 minus 3 is 3. 3 plus 7 is 10. Oh my gosh, 10 minus 10, it's 0. Wow, look at that. Usually kids will say, I think I've got it. I think I can figure out the rest of them. I hope so, but we'll finish them up. Any questions so far? Again, using that golden equation, oh my gosh. That unleashes so much for you. Look, we're going to say, you got to find f of 4. Here's Roman numeral number 3. F of 4 was 10 plus 8 to 4 of f prime of t. Once again, we wince at that. We'll go, oh man, the integral's written in this unseemly way where, you know, really we'd like to see the low number at the bottom, the 8 up high. Change it. Just change it. Flip your bounds. And there you go. And then kids will go, okay, so I'm going to go from 4. Well, 4 is right over here. I'm going to go from 4 to 8. Hey, we've got less to deal with. That's negative 3 plus 7. And a lot of times kids are going to be like, oh my gosh, why didn't you just add them together in one step? Negative 3 plus 7 is just a 4. Yeah. 10 minus 4 is 6. Look at that. Might guess that the last one might be the shortest. You know, is it just going to be a 3? Yeah, well, the area from the 4 to the 8 is going to be a 7, but we're going to still have to subtract it, aren't we? Because we're flipping the bounds. So kids will be like, is the last one 3? You bet. You bet. Why? Look at this. Because you could say, well, f of x was 8, or sorry, not 8, it was 10, plus from 8 to x of f prime of t. You guys get what's going on. You do this enough times, and forgive me, that's a 6 right there. Wow. Just want to put in a little bit of space. You know what? Let me see if I can nicely, gently do this, perhaps. Will it? It might not let me. Yeah, there we go. Wish I could do that in real life. That would be cool. All right, but in any event, let's see what we've got. Hold on. Gotta go back to our draw menu, come back to the blue. All right, so it's 10 minus from 6 to 8. Such good things to talk about right here. We saw that that was 3, and that's a 7. So that's what we have for f of 6. Got a little sloppy right there. We doing okay? All right, that's the end of the video. Did I reverse it?
10 minus 7 and then.
Oh, it's 10 minus 7. Oh my gosh, good thing you guys are here. I didn't stop the video. There we go. So good thing I've got my students here. They saved the day once again. All right.